Across an area larger than the continental United States, the ground is supposed to be permanently frozen, not seasonally, not intermittently, permanently, locked in a state of deep cold that has persisted for tens of thousands of years, holding the landscape rigid, the soil solid, and the surface stable enough to support forests, rivers, roads, and cities built directly upon it. That ground is thawing. In the summer months across Siberia, researchers flying low over the West Siberian plain have documented a landscape that from the air appears almost lunar, pocked with irregular depressions, collapsed terrain, and dark water-filled craters where solid earth existed only years before. On the ground, the scale becomes personal. Buildings tilt at angles their architects never intended. Roads buckle without warning. Coastlines that have been geographically stable for recorded human history are retreating by several meters per year. And from the surface of certain lakes, bubbles rise continuously, day and night, through water that should by all thermal logic remain near freezing. Those bubbles are methane. And what they represent, in terms of volume, in terms of chemical composition, in terms of what their release means for the trajectory of the global climate, is one of the most consequential and least publicly understood questions in contemporary Earth science. The permafrost beneath Siberia covers approximately 65% of Russia's total land area. Within that frozen ground, accumulated over millennia of Arctic cold, lies a quantity of organic carbon estimated by leading research institutions at more than 1.5 trillion metric tons. That figure is not a projection or a model output. It is a measured estimate derived from soil core samples, satellite analysis, and decades of field research conducted across some of the most remote terrain on Earth. It represents nearly double the total amount of carbon currently present in the entire atmosphere. That carbon is not stable. It is thawing, and as it thaws, microbial activity converts it into carbon dioxide and methane, greenhouse gases that feed directly back into the warming that triggered the thaw in the first place. Three questions define the full weight of this situation. How did this much carbon come to be locked beneath the Siberian surface? What is the precise mechanism by which it is now being released? And at what point does this process shift from a measurable trend into something that operates beyond the reach of human intervention? The permafrost of Siberia did not form quickly. It is the product of a climatic era, specifically the Pleistocene epoch, which began approximately 2.6 million years ago and ended roughly 11,700 years before the present. During this period, much of the northern hemisphere experienced repeated glacial cycles, and the land masses of northern Asia were subjected to extreme and sustained cold. Unlike large portions of North America and northern Europe, Siberia was not covered by glaciers during the last ice age. It remained cold but exposed, a vast, dry, wind-swept landscape known in the scientific literature as the mammoth steppe. This steppe supported remarkable biodiversity: woolly mammoths, woolly rhinoceroses, cave lions, and enormous herds of bison and horses. Grasses, sedges, and flowering plants grew prolifically across the surface, fixing atmospheric carbon through photosynthesis in enormous quantities each growing season. When these organisms died, the extreme cold of the Siberian climate prevented their complete decomposition. Organic matter accumulated in the soil year after year, century after century, millennia after millennia, frozen into the ground before microbial activity could fully break it down. The result was the formation of a unique geological layer called Yedema, ice-rich, organic-laden permafrost that in some locations extends to depths of 25 to 30 meters. This is not merely frozen soil, it is a chemical archive. Preserved within Yedoma are intact plant material, animal tissue, pollen records, and an unbroken organic carbon inventory that predates human civilization by tens of thousands of years. Scientists have extracted intact woolly mammoth specimens from Yedoma deposits with soft tissue, hair, and stomach contents preserved in states that would be impossible in any warmer burial environment. The Yedoma layer is also extraordinarily vulnerable. Its stability depends entirely on the maintenance of temperatures below freezing throughout the year, and those temperatures are no longer reliably maintained. The Arctic is warming at a rate approximately 4 times faster than the global average. This differential is not disputed in the scientific literature. It is a measured phenomenon confirmed by multiple independent datasets from surface stations, weather balloons, and satellite sensors. The causes are well understood. Chief among them is Arctic amplification, a feedback dynamic in which the loss of sea ice and snow cover reduces the reflectivity of the surface, causing it to absorb more solar radiation, which generates additional warming, which causes further ice and snow loss. As air temperatures rise, the depth of the active layer, the uppermost portion of permafrost that thaws seasonally and refreezes each winter, increases. In practical terms, this means the frozen ground is being attacked from above year after year, with each warm season reaching slightly deeper into the previously stable permafrost column. When the organic material in thawing permafrost is exposed to liquid water and microbial activity, decomposition begins. In aerobic conditions, where oxygen is present, the predominant product is carbon dioxide. In anaerobic conditions, beneath lakes, in waterlogged depressions, in the oxygen-depleted environment of saturated soil, the decomposition produces methane. Methane is, over a 20-year period, more than 80 times more potent as a greenhouse gas than carbon dioxide. The thermokarst lakes of Siberia, bodies of water that form as ice-rich permafrost thaws and the surface collapses, are among the most methane-productive environments on Earth. Research conducted by teams from institutions including the University of Alaska and the Stockholm University has documented methane ebullition, the process of bubble release, from Siberian thermokarst lakes at rates that significantly exceed earlier model predictions. In certain areas, the methane concentration above these lakes is measurably elevated compared to background atmospheric levels. Abrupt permafrost thaw, the sudden collapse of terrain rather than gradual surface warming, is emerging as a mechanism of particular concern. Where eudoma deposits exist, thaw can be nonlinear. A thermokarst lake, once formed, actively accelerates the thaw of surrounding terrain through lateral heat transfer and the thermal properties of liquid water. The process self-propagates. The lake grows. The methane release increases. The dynamic is local in origin, but cumulative in effect. For the Russian state, permafrost is not merely an environmental concern. It is an engineering reality upon which the material foundations of an entire regional economy rest. Approximately 35,000 buildings in Russian Arctic cities are constructed on permafrost foundations. Norilsk, Yakutsk, Vorkuta, Salikard. These are not small settlements. They are industrial cities, some with populations in the hundreds of thousands, whose infrastructure was designed around the assumption that the ground beneath them would remain frozen indefinitely. The pipelines that carry oil and natural gas. From Siberia's vast hydrocarbon fields to processing facilities and export terminals are similarly dependent on frozen ground for structural stability. 2021 study published in the journal Nature Reviews Earth and Environment estimated that infrastructure damage from permafrost degradation in the Russian Arctic could cost the Russian economy between $84 and $121 billion by 2050 under moderate warming scenarios. These figures represent direct structural damage alone, the cost of repairing or replacing buildings, roads, pipelines, and foundations, and do not account for the broader economic consequences of disrupted industrial operations or displaced populations. In 2020, a fuel storage tank at a Norilsk nickel facility collapsed after its permafrost supports gave way, releasing approximately 21,000 metric tons of diesel fuel into local waterways. Russian authorities described it as the worst environmental disaster in the Arctic in decades. The immediate cause was structural foundation failure. The underlying cause was permafrost degradation. The core scientific concern about Siberian permafrost thaw is not the release of carbon per se. It is the feedback relationship between that release and global warming, and the degree to which this feedback could amplify warming in ways that exceed current climate projections. The majority of integrated climate models used by the Intergovernmental Panel on Climate Change have historically treated permafrost carbon release as a gradual, predictable process. More recent field data suggests that abrupt thaw mechanisms, thermokarst formation, retrogressive thaw slumps, and lake expansion could release carbon at rates faster than models have incorporated. A 2019 commentary in the journal Nature, authored by a group of permafrost researchers, argued that the IPCC's assessment framework was underestimating permafrost carbon feedback and called for its more complete integration into mainstream climate projections. This is not a fringe position. It represents a measured scientific argument from researchers whose careers are built on the direct observation of these systems. The disagreement is not about whether permafrost carbon is being released. It is about how rapidly, through which specific mechanisms, and with what degree of self-reinforcing momentum. The concept of a tipping point, a threshold beyond which a system's internal dynamics drive it toward a new stable state, regardless of external input, is directly relevant here. Whether Siberian permafrost thaw is approaching, has reached, or remains below such a threshold is a question that current monitoring systems cannot definitively answer. What is known is that the monitoring infrastructure across the Siberian interior is sparse relative to the scale of the system being observed, and that baseline data from much of the region extends back only decades, not centuries. A persistent misconception in public discourse about permafrost is that its significance is primarily atmospheric, that the concern begins and ends with greenhouse gas emissions. The reality is considerably more complex. Thawing permafrost releases not only carbon gases, but also other long-frozen materials. Ancient bacteria and viruses preserved in permafrost for thousands of years have been documented as viable upon thawing. In 2016, an anthrax outbreak in the Yamal Peninsula of Siberia killed a child and hospitalized dozens of people after a heatwave thawed permafrost and exposed a reindeer carcass infected with Bacillus anthracis spores that had been frozen for an estimated 75 years. The event was not a theoretical risk scenario, it was a documented public health incident with a confirmed permafrost origin. Researchers have additionally revived ancient giant viruses that infect amoebae rather than humans, from Siberian permafrost samples tens of thousands of years old. These specific organisms pose no direct threat to human health, but their viability after such extended preservation periods demonstrates that the frozen ground of Siberia functions as a biological repository as much as a carbon reservoir, and that the contents of that repository are not fully catalogued. The trajectory of Siberian permafrost over the coming decades will be shaped primarily by the trajectory of global average temperatures, which is itself determined by the pace and scale of decarbonization efforts across the global economy. This interdependency is not a circular argument, it is the actual structure of the problem. Under the most optimistic warming scenarios, in which global emissions are reduced rapidly and temperatures are stabilized near 1.5 degrees Celsius above pre-industrial levels, permafrost loss is projected to be significant but potentially manageable, affecting perhaps 10 to 20% of current permafrost area by 2100. Under higher warming scenarios, the projections are substantially more severe, with widespread permafrost loss across much of Siberia and accelerating carbon release that would itself contribute additional warming fractions to global temperatures. The honest scientific answer to what happens next is a range, not a single projection. The range is wide. The lower end of that range is manageable with difficulty. The upper end involves dynamics that current civilization has no tested framework for addressing. The distance between those two ends is determined largely by decisions being made now, in energy policy, in land use, and in the prioritization of scientific monitoring infrastructure in some of the most remote places on Earth. There is a particular quality to the Siberian landscape in late summer, the way the light falls flat and gold across terrain that appears solid but is no longer trustworthy underfoot. The rivers run brown with sediment from collapsing banks. The forests lean at angles that have nothing to do with wind. The lakes breathe methane into air that carries it upward into an atmosphere already under pressure. Beneath that surface lies an archive, one that accumulated over tens of thousands of years of cold, death, and preservation. One that contains the carbon of vanished ecosystems, the genetic material of extinct species, and possibly biological agents that the modern world has never encountered in active form. Humanity did not create this archive. It inherited it, along with the climatic conditions that are now unlocking it. What Siberia is telling us is not a prediction. It is a measurement. It is the present tense account of a system responding to conditions already in place. Not conditions that might arrive, but conditions that arrived years ago, and whose consequences are now visible from the air, measurable, in bubbles rising through frozen lakes, and quantifiable in the tilting foundations of cities built on ground that was never supposed to move. The permafrost does not negotiate. It thaws according to physics, and physics does not wait for consensus.